Hi everyone, how are things? Welcome to the ultimate RAG tutorial. This is the most extensive, detailed, and hands-on tutorial that you will probably find anywhere on internet, which tries to explain retrieval augmented generation, aka RAG. This tutorial aims to make you experts at building solutions and applications which leverage the generation capabilities of modern large language models. So, let's go. Alrighty, so the idea is this tutorial will be split in about 9 chapters. Yeah, I know, that is how extensive it's going to be. The first 5 chapters will concentrate on basics of RAG for everyone. We'll cover the why and what of retrieval and generation systems and will slowly build up to implement a basic RAG application. For that, we'll take a step back and start getting into the nuts and bolts of retrievers, including RAG architecture, evaluation of RAG systems, knowledge extraction, storage, and much, much more. The later chapters, starting from 6 onwards, is where we will build into more advanced RAG concepts and aim to take the viewers towards expert knowledge. So, yeah, there's a lot in here. So, please feel free to jump between chapters depending upon what you are seeing and leverage the learnings as per what you might need at this stage. All the code, architecture diagram, and lots of other stuff for this tutorial will be on GitHub, and I will put the link in the description. So yeah, really excited, and let's get started. So let's start with ground zero, or so should I say, where RAG system became as popular as it is today. So retrieval systems are an age-old concept anywhere in your daily life where you might work with a sophisticated system and interact with it in natural language or pseudo-natural language to access useful information is a retrieval system. Some examples are search, it's a retrieval problem. Accessing a database using SQL is also a retrieval problem. So yeah, though retrieval as a discipline of science and tech has been under study and application for ages, but what made it so popular in last 1 to 2 years is the advent of age of large language models. So large language models, or GPT-4, took the whole world by storm in 2021. What actually amazed everyone was we now had a system which we could interact with in natural language and could get a human-like response. Moreover, these language models were excellent in terms of information tasks like text summarization, code generation, cross-domain knowledge transfer, understanding multimodal responses, and so on. Though the initial experience was outstanding, when teams planned to deploy this into enterprise or production applications, they learned a big flaw about them. The problem with LLMs is that they have been trained on openly available data like internet blogs, Reddit forums, Wikipedia, open research papers, open domain books, etc. That means they do have a good understanding of how the world works or about general knowledge like which country is Paris in, so they make an excellent general knowledge retrieval systems. But when it comes to domain specific or deep knowledge like healthcare, insurance, banking, or organization specific knowledge, they don't have much of a knowledge base to rely upon. The problem is particularly grave when someone is trying to deploy an LLM for a knowledge retrieval task, which is for an institution or domain which has its own proprietary knowledge base for organizational function. Let's take an example to understand it better. If you ask ChatGPT, what is the capital of France, it answers it with ease. But if I ask it, who is responsible for approving home loans at XYZ bank, it might not answer it, or it might what we call hallucinate. It might give an answer which is totally random. Now, why is that? It's because the answer of the question that who is responsible for approving home loans at XYZ bank is probably in one of the documents deep within the knowledge base of XYZ bank. So this failure of LLMs raises deep concern around how to deploy LLMs for domain or organizational use cases. The answer is Retrieval-Augmented Generation. RAG, or Retrieval-Augmented Generation, is a process or protocol through which we enhance the knowledge or context of an LLM, based on which we can help an LLM answer questions which are either known in its knowledge base, or LLMs find it hard to access that knowledge base. The intuition that you might want to build to understand a RAG-powered LLM is that a generalized knowledge base of an LLM is like its long-term storage. It stores world knowledge which it has been trained on. Now when we expect an LLM to solve a problem, or when you ask a question from an LLM, the LLM tries to access this knowledge base of this long-term memory, but that knowledge either might not exist in the long-term memory, or the LLM might find it really hard to access that knowledge snippet. due to which it might either not answer the question or hallucinate and give a wrong answer. Now, RAG adds a short-term memory or RAM to a LLM. Based on what question is asked, the retrieval system adds knowledge which is tailored for the existing question to LLM's current context. It makes it much more likely we will have an accurate and productive interaction with an LLM. Let's understand this much better by building a basic RAG pipeline. Alrighty, so let's get started with this short implementation of a basic RAG system. The idea of this small tutorial is what more points were discussed before in this video. We'll try to see that in action and see a simple retrieval augmented generation in action. So proceed with the code and implementation and everything else. Let me move this here. Now this is a simplistic architecture of a RAG system, okay, which works with large language model as a generator, and the large language model is supported by a retriever and helping it enhance its current knowledge base. Okay, so if you see, the way it might happen is we'll take an example of some other things that we discussed before in the video. Suppose the user asks a question about who currently manages the lending in XYZ bank. So this question goes to the retriever. Retriever takes that question, goes to the current knowledge base of the XYZ bank. The assumption is this retriever and this complete application is for an XYZ bank. It fetches the corresponding document that might be needed to answer that query, takes the document and adds the retrieved context to the context of large language model, and then the large language model takes that context that has been added to its overall next token response context numbers and helps us generate a response. Okay, so this is if you try to understand it, this is how the complete retrieval augmented generation mainly operates. Okay, and then everything right from a basic RAG application to advanced RAG application is in essence this. Okay, then there are nuances, and as we have discussed before, and as everyone knows, nuances are what differentiates between a great implementation to an implementation that works very well on a notebook or a computer, but doesn't well that well on a production. Alrighty, let's proceed. The first is let's probably pick a use case. The use case that I picked here is we will build something that is called as archive bot essentially. So online we do have archive.org where there are like lots of peer review and sometimes peer review research papers are uploaded, and we do have a data set essentially which is called, let's have a look at it. Okay, it's called the archive metadata OAS snapshot. We can even try and have a look at it. Archive data set. Okay, so this is data set that I spoke about. It's some Kaggle. Everyone can go and download it. I will mention this link down below in the description. Feel free to check this out. So yeah, what I've done is I've downloaded it. I've unzipped it, so it gave me a JSON which was around 4 GB in length. And just to check what actually exists in there, this is a function that we have written which helps us see multiple records within the archive file. Let's have a look at it. So yeah, we're looking at three. This is a complete structure of the JSON document. It has an ID, it has a submitter who actually uploaded that particular research paper, then we have a title of the research, and post that we also have the abstract of the research paper. Alrighty, so this is what we have for n number of research papers in there, and this is going to be our knowledge base based on which we will have developed a retriever which will be leveraged to add context to the large language model. Alrighty, so and what I'm calling it is an archive bot, which could be probably leveraged by anyone trying to understand more about research paper or ask questions about research papers and so on and so forth. So very simple case for us to understand how retrieval augmented generation essentially works. Now let's move ahead. Okay, the first one we'll do is try and understand basic retrieval without LLMs. Right, as I mentioned before, retrieval is a very age-old, tried and tested engineering and science skill. So we'll first of all try and develop a basic retrieval based on this data set that we saw. Step 1, we create an index and get term frequency, inverse document frequency for each article or abstract. Okay. Now, what is a TF-IDF or term frequency inverse document frequency? Let's check that. So this is a link that I have shared. Please feel free to check it out. But in essence, a TF-IDF is a way of identifying that out of a text corpus, if we have different words, after removing the stop word like is, are, the, how many words exist in that word, in that statement, which are very unique to that statement, but are not present that much in the rest of the corpus. Okay, so this is called a term frequency, inverse document frequency. So as I mentioned here, term frequency, well, we're looking at the frequency of particular term. You're concerned with related to document. There are multiple measures. Okay, and inverse document frequency. Inverse document frequency looks at how common a word is amongst the corpus. Okay, so so we see if to term frequency we see if there is a word which is mentioned multiple times in a particular, let's say, statement, but it's not mentioned that much overall in the corpus. It's become a very important part of that statement. So to calculate TF-IDF, we basically multiply both of them and kind of get something called as a TF-IDF score. So in a sense, I won't talk more about it because it's a very simple concept. Please feel free to read through it. But that's what we are going to do. That's what we are going to use to create an index. And we'll create an index and then we'll get a TF-IDF for each article or abstract. This is the code that we will use. What this code essentially does is it takes the document, it for each line essentially in that document, or for each paper in that document, it loads it using JSON download. It kind of creates a particular text field by appending the article and the abstract together. So this is what we will use to for each paper. We will have the article and abstract and title appended together, but that is what's going to be used to calculate TF-IDF. Post that, we'll also have something called as metadata, in which you will add the title and abstract. And finally, we will use something TF-IDF vectorizer. Again, scikit-learn, a great library. Lots of people who are probably from the data science world will know about it. Is used to vectorize all of these documents. Okay. Now, which we save it as a pickle file. So that's as simple as it is. Essentially, like each paper is taken and its title and summary is appended together. Relative to the all of the everything in that JSON file, we calculate its TF-IDF score and we store all of that. Okay. Now, final thing that we have, as I mentioned here, is a pickle dump. In that pickle dump, what we have is for each paper, we have the vectorizer, we have the TF-IDF matrix, and we have the metadata. That is what we have stored, but we are mainly concerned with the vectorizer and the metadata. So in here, basically, when we run it, I already run it before. It takes a bit of time. It's reading the documents in here. It's probably a few more seconds. Once this gets done and we have the vectorizer for each of the papers, we create a simple user experience, user interface using Gradio, a really popular interface creation tool for people who don't want to develop a full-blown user interface using JavaScript and React. Alrighty, so it's done. We have the index created and saved. So our very important part is done. Now let's basically run this, create the interface. Alright, it's loading the index and hopefully creating an index for us. Alrighty. Archive paper search using TF-IDF. So as I mentioned here, let's search for something. let's search for probably, I've been reading a lot about dark matter. Let's search dark matter in planets. Okay, remember, right now it's just doing a text search. Okay, text search in a different way, but in essence it's a text search. It takes the words and what you are asking for, and all of the corpus that it has, it goes and tries and find those words, and it has a way of basically wherever it finds those words which exist, it basically will rank them in a particular way that we mentioned cosine similarity and present to us. So I've mentioned dark matter in planets, and I've clicked on submit, and here it's processing it. Let's see the results that come out. Okay, we got some results. Alrighty, so let's go right to the top. Okay, result one is dark matter and the habitability of planets, and gives an abstract. Okay, not bad, right? I searched for dark matter in planets, gave me the first one was that. Result two, light dark matter accumulating in planets. Not bad. Result three, unified distribution of dark energy and dark matter. This doesn't have planet, so therefore it got a lower score already. So you got in essence how a basic retriever or text-based retriever might actually work. Again, right now it's just a retriever, right? So one thing to understand, it still doesn't have a conversational quality. Why are large language models so popular? Is because you can have a conversation like a human to it, and you don't need to have a binary coded answers to it where every time it will respond in a particular way. It's literally has a bit of dynamic way of answering questions, but also you can add a retrieval to it. Like giving you an example, if in here I ask a question, can you recommend some papers on dark matter? Already, so if I ask this question to a few of my friends who are physicists, they will probably say, "Oh, yeah, definitely, these are the three papers, right?" Or, "Oh, yeah, sure," something like that, right? But when this is something just which is a retrieval system, so it highly won't. So I will click on submit. Okay. Shut up and let me think, or why you should work on the foundation quantum mechanics as much as you please. Just flipping like it's very likely, okay, whatever, and so on and so forth. We don't have anything here. Introduce and work on dark matter. Okay, we found something on dark matter. Solar system. As you see, what we just got as results. We didn't get a conversation. We didn't get a further details around it, and that is why we basically introduced large language models into our workflow. All right. Now, next move forward. And let's try and build a large language model powered chatbot on the same corpus that we basically saw before. Okay, so again, the whole code is in here. I have written this code to run on Azure OpenAI, but the same code can be leveraged if you are using it for OpenAI, or you are using even it for Anthropic. The models underneath don't matter that much. The prompting and the corpus actually matters at this simple scale, at least. So simple code. Again, as I mentioned, I'll just quickly run through the code. It takes the pickle file, takes the vectorizer, takes the TF-IDF of the matrix, searches through the whole of the corpus, and gets the corresponding result, takes the top paper that it could find, and adds its title, abstract, and the corresponding cosine similarity score to the context of the large language model, right? So here is a retrieve models are basically joined in here, and then we have something that is called as a system message. A system message essentially is where you tell a large language model how it should basically respond. So it's a simple message. It's basically you are an archive bot and you do some stuff, but your goal is use the information from the papers. Only mention limitization. The paper totally contain no relevant information. The paper partially addresses the question. So ideally, one thing that you have to understand is now you have to play with multiple stuff, because the large language model, in essence, it also has its own information. So you have to explicitly mention that it should use the context or the information that you are adding from the retriever system. So there's important pointers around it essentially, which I've kind of mentioned here. Feel free to use it. Feel free to further enhance it. Again, working with the prompts in a very good way is another huge topic. We might have that also a topic of discussion sometimes later in another series of lecture. Another thing that we do is we also add a chat history. So chats keep on happening, and we want to make sure that the large language model has the context of the conversation that we have happened so far. So we keep on adding the chat history to the conversation that we keep on having. So that's about it. I think it's that's what we are doing. We're just playing with the large language model here, and we kind of launch another Gradio UI. It's loading the index. Hopefully we should have the UI anytime now. The fun part is, and the most interesting part of the whole process that I find is that how much large language models have made us take human-like conversation with a system for granted. Like when I was doing this retrieving thing before, which doesn't have a large language model, I was feeling, oh wow, it's so outdated. But it does the job, right? It does the job, but this human experience, the user experience that you get here. Already, so let's ask it a question, please. Papers on dark matter. Okay, let's see. I'm asked you to please recommend me some papers on dark matter. We have a large language model in the backend. Let's see how it answers that. Okay, here we go. Here are some relevant papers on dark matter that you find interesting. Comments on recent work on dark matter capture in solar system. Unified distribution on this, and you see how it has formatted it for me. It has not just taken a chunk from the dump and put it in here. It has basically formatted it like how a good conversational agent or a good person who's a knowledge expert might put it in. And I will Apple full edition. So again, see papers, I can further ask it other insightful question. But we ask it which of these papers I should start with. Oh, please mention also mention why. Okay, I got about an answer. Okay, among the paper mentioned, I recommend starting with the unified distribution of dark energy and dark matter. Okay, so before it kind of gave me 3 papers. Okay, and the second question that I asked is which of these papers I should start with, and please justify it. And if it was not a large language model, it would have never been able to justify stuff, because here it's bringing its own internal knowledge with the addition context that I have. And so it's given me, okay, you should probably use unified distribution of dark energy and matter. Reasons to start here: foundation understanding, comprehensive overview, contemporary relevance, the interplay between dark matter and dark energy, theoretical insights. Now, again, there are lots of further nuances in here which we have to play with. Like, for example, how do I make sure that the follow-up questions, it only still leverages probably some other knowledge base, or when I ask some. So there are other factors which have its own system architecture, system knowledge around it. But for a basic example, I think everyone probably got how a basic RAG system mainly works. So it's a retriever which helps an LLM knowledge base with a particular context or a particular knowledge which is relevant to the problem that we are trying to solve, and post that using prompting and other strategy. We make sure that large language model ends up using only that context to answer the questions which are relevant. Alrighty, so that's about it. That's the demo, and that's also probably the end of this video, and this part of the basics of Retrieval-Augmented Generation. And I hope you had fun. All the links that I mentioned and all the resources that I mentioned, everything will be in the description. Also, this code and this notebook will be in the will be on a GitHub repo and will be mentioned in the description so that everyone can leverage it. The best way I will suggest everyone is once you listen to the first part of everything before this demo happen, open this notebook, think of something else, think of some other problem that you want to solve. Maybe right now I use archive dataset, you might end up using Polygram blogs or some other set of blogs, and think of a problem that you might reckon a large language model powered by a rack system might help solve, and try to solve it maybe using the same notebook, make some additions, and that's how basically you will at least start becoming comfortable with how a retrieval augmented generation system works. So that's it for me. I hope this was able to convey to you how a rack system work. There is plenty more to come. We will further delve deeper into this system. Will kind of make it a much more robust production system. Think of things like evaluations, how do we scale it for multiple use cases, and yeah, a lot more. So that's about it. See you next time. Bye.